Okay, very good morning to all of you. I think I'm audible. So I'm sharing the QR code, give the attendance, and then we will start. Wait, let me share the QR code. Just take down the QR code, give the attendance, then we will start. So in my last class, I discussed with you about digital frequency meter. Okay. And what else I discussed? Two topics I have discussed with you. One is digital frequency meter, and another one is its construction details and all. And another one topic is what? Tell me, let me see whether you remember or not. Which one?
Voltmeter.
Yes, true RMS reading voltmeter. Okay, so so what is the use of digital frequency meter? Anyone tell me where we can use it? Digital frequency meter? Any one of you? Just tell me the answer where we can use digital frequency meter. What is the purpose of using digital frequency meter? Kindly reply. Tell me the answer, otherwise I cannot start. What is the use of digital frequency meter? Yes.
Ma'am, to convert analog or sinusoidal signal into the digital signal.
Okay. Okay. So basically, we need to, it is represent, or you can say digital frequency meter are basically used to measure sinusoidal waveform, right? It's using schemic trigger and flip-flop and gate, everything. Okay, so whatever we are getting in the counterpart, that is we require here. So just that schematic diagram which in yesterday's class I have shown you in previous class, so that you need to follow. Okay. Okay, so let's start. Lakshmi, I will add you. Don't worry. Give me some time. I will add you in the LMS portal. Okay. Okay, let's do. Okay, today I don't have such PPT, so I will just make you understand everything in the whiteboard. Okay, so let's do. Now, in as per your syllabus, in module 2, we have completed the 2 topics. Okay, if you check it out. I'm going just strictly with the syllabus. Okay, so in module 2 we are done with 2 topics. One is true RMS reading, second is digital frequency meter. Our third topic is high frequency measurement. So which we will start today. It's a big topic, high. So just listen to me very carefully. We will do some problems also side by side, so that this doesn't become so boring. Okay. Acha, wait for the second. Let me see whether my recording is recording on. Okay. So in high frequency measurement, first of all, when I'm speaking about high frequency, that means there should be a particular range. Okay, the range of measurement should be there. So what we need to do here, in this particular topic, we need to measure inductance, capacitance, resistance, both the 3. What I told you, inductance, capacitance, okay, and resistance. This both thing we have to measure, all the 3 things we have to measure, but in the frequency range, in the frequency range of 0.1 to 100 megahertz. Okay, so this is my frequency range within which, or this is the high frequency measurement range, okay, within which we need to measure the inductance, the capacitance, the resistance. Now, definitely the bridge methods can be used. Previously, we have learned in module 1 for measuring frequency, we have some bridges. So, bridge methods can be used in this frequency range, but these methods give, much error result. So, what we have taken some special kind of methods for measurement of high frequency in this range. Now, some of the special effects which are predominant in high frequency measurement, what are the number one, you can say, it is what are the special problems that come up. One is high reactance. Okay, one problem is high reactance. High reactance due to stray series inductance and its variation with frequency. So our first special effect is high reactance. Second special effect is, you can say, low reactance. Low reactance, that is due to the stray shunt capacitance. So this high reactance was due to series inductance. Okay, series inductance. And this low reactance is due to shunt capacitance. Okay, shunt capacitance. Then third is increase of effective resistance with frequency, and fourth is again increase of effective resistance due to proximity effect. Okay, and fifth is variation of dielectric loss of capacitors with frequency. So all these 5 points come up with both of these. Let me write here. This is also increase of resistance. This is increase of resistance due to what? This increase of resistance with frequency. If my voice lags, then do let me know. Okay, with frequency due to skin effect. So skin effect is an effect which occurs. And fourth is again increase of resistance. So I'm giving the inverted comma on account of proximity of effect. So you can say, or you can say due to proximity effect. Okay, due to proximity effect. And third is, sorry, and fifth you can take variation of dielectric loss. Okay, variation of dielectric loss. So these all are the special effects which are predominant at high frequencies. Now these effects make the high frequency measurement complex. Simple. All these effects, if we found in high frequency measurement, then these make the high frequency measurement somehow complex. Okay, so if the bridge circuit are used as high frequency, then elaborate shielding measure arrangements have to be adopted to nullify all these factors. Okay, if we use some bridge. So the normal approach for measurement of high frequency is to adopt such methods which are as simple as possible. Okay, so that the effect of this electric and magnetic fields can easily be removed. So since errors of the order, some errors you can say 1 to 5% are acceptable, okay, in measurement of frequency range. So methods used to involve use of very simple apparatus. Okay, so what are the simple apparatus used? Let me go to the next page. Let me tell you. So simple apparatus that may be used here. So I told you what are things we have to measure. We have to measure resistance, we have to measure inductance, we have to measure capacitance. So first we will take a set of inductors. Okay, set of inductors that will range from some 1 microhenry to 10 millihenry. Okay, this is for measurement of inductors. Second, we will take variable air capacitor. Okay, variable air capacitor of maximum capacitance. You can take some 1000 picofarad, 1000 pf. Okay, and third one is a decade resistance box we have to take. Okay, decade resistance box of resistance up to how much? Up to 100 ohm. Okay, so these are the range with which we will work. And fourth one, if required, we will use electric ammeter, that is called thermoelectric ammeter, in order to indicate some resistance conditions. That is optional. Now let us come to the resonance methods in case of high frequency measurement. Okay, so let me come to the okay, first is resonance method. Okay, what is this method, resonance method? Now, most of the methods used for high frequency measurements, they use what? Series RLC resonance circuit. Okay, so that is the resonance method. So let me show you the circuit actually. So there will be an oscillator. Okay, I cannot draw so much proper diagram, so kindly bear with me. So first of all, let me draw oscillator. So here we will use RLC resonance circuit. So resonance, I think you have learned before also. So this is your output coil. Okay, and we will connect definitely ammeter and voltmeter here, and a resistance also. So we will be having here an ammeter that is called a milliammeter, and here you will be having a resistance. And definitely you have to check out where the RLC we are connecting. So this is my milliammeter, I'm right MA. This is my resistance, okay? And I have to now connect a capacitor here also. This is here somehow, capacitor, okay? This is my C, and I need a TVM. So TVM, just now I told you what is TVM. thermoelectric ammeter. So let me show you this TVM here. So this is TVM, or you can name it as VTVM. We can also call it as VTVM. Okay. Or you can say it as thermoelectric ammeter. Okay, this is my inductance L, and this is my output coil. This is my output coil, and this is my oscillator. So I hope this picture is clear to you all. So this picture is RLC resonant circuit. Okay. So see here, here we have drawn a resonance circuit. Now, minutely see this picture. What is there? The EMF for the coils for the circuit is obtained by coupling the coil L with the output coil of the oscillator. Have you seen here? Let me change the color of the pen. See here, oscillator is having an output coil, this one, and this is the coil of the inductance. So what is happening here? EMF is induced here, okay, by coupling the coil L with the output coil of an oscillator. Understood this portion? Secondly, a loose coupling definitely is desired. Why? Because to withstand with the changes in condition of the RLC circuit. So you have to see that a loose coupling is desirable in order that the changes in conditions of RLC circuit that does not affect so much the oscillator circuit, because there are two parts. One is this RLC portion, one is this oscillator portion. Okay. So a tight coupling on the other hand will affect the oscillator. So whatever coupling we are doing here between the output coil and this inductance, that has to be a bit loose. Okay. So tight coupling is not so much desirable here. So definitely the coupling should be such that it does not affect the oscillator circuit. The resonance is obtained either by variation of frequency of the oscillator, this is connected here, okay, or by variation of the capacitance. This is the capacitance part. So resonant conditions are indicated by what? Indicated by this one, this thermal milliammeter, this one, okay, ammeter connected in the circuit. So whatever resonance we will be getting, that will be observed in this milliammeter. So a thermal milliammeter is necessary. Why we need thermal milliammeter? Because it can work nicely in the high frequency regions. Okay. So under the resonant conditions, the milliammeter indicates maximum reading. Okay. So which condition? Resonance condition. Under the resonance condition, if you say, this milliammeter gives maximum reading. Okay. Maximum reading. Now, in practice, it is convenient to use this VTM or VTVM, as I told you, which is connected across parallelly with the capacitor. And why it is connected? Definitely to indicate the resonance conditions. Okay. Since ammeter introduces an extra series resistance, you see here, resistance connected here in the circuit. So resonance is indicated when the voltmeter reads again the maximum. Okay, so here it's a work of that both the things changes we will see in both the reading device. So now here it is very interesting to note that the circuit condition which gives maximum current, okay, that is not same as what it's showing during the maximum voltage across the capacitor. Okay. So what we have to see, it's assumed every time that when the voltmeter, that is this TVM, you can see connected across parallel to the capacitor, that shows the maximum reading. That means what it will show? The voltage that is flowing through the capacitor. So the circuit is having here maximum current, that is the circuit is working under resonance conditions. So these are the assumptions sometimes we have to take. Now, suppose we are taking resonant methods. So resonance curve we can see here. So curve that we will get here, it will be somehow highly picked, okay, and highly selective, which is having a high Q factor. Q factor means quality factor. Okay, quality factor. This Q factor is also important in case of resonance method. And the readings which are taken, that is somehow near to the resonance points. Okay, and to satisfy all these conditions, we have to take the, this is the assumptions that we have to take in this resonant method, that the current which we will measure, that has to be 50% of the maximum value of the current. So basically, keeping your mind in one thing, this resonant method is used to measure the high frequency range. Okay, so in this case, we are having this RLC resonance circuit, okay, where a coupling is being formed between the oscillator and this RLC part. Okay, and rest of the things and resonant conditions, the milliammeter is giving us the maximum reading, and this TVM is also giving us the maximum reading, which is the voltage across the capacitor. Now, next, let us move to the measurement of inductance. Okay, as I told you that we need to measure, inductance in this frequency range. So what is the frequency range? I'm going to the first page. My frequency range is 0.1 to 100 megahertz. Okay, in this range, I have to measure the inductance. So let me move on to the next page. So now I will take measurement of inductance. Wait. Okay, so measurement of inductance, I'm writing here. Now, in measurement of inductance, definitely you have to draw a circuit. The circuit will be similar to that of the RLC resonance circuit, which just how I told you. Only the difference I'm telling you. There will be an oscillator, okay, and oscillator will be having an output coil. Okay, this is my output coil. I'm writing like this, output coil. Then you will be having a LC, which is your L. This is your L, and you will be having, here will be no R. Okay, it's an inductance. So capacitor will be connected here in parallel with the inductance, and here you will be having a VTM, sorry, TVM or VTVM, whatever you can say. So this is the TVM, okay, or the thermoelectric, which I told you. So this is the picture of measurement of inductance. Okay, so here is a simple circuit, and in this coil under measurement, definitely loose coupling is required. And the dial of the oscillator here will be calibrated in terms of frequency. And you see here a variable capacitor. There's a variable capacitor, so you can click this kind of arrow here, and it is used for obtaining resonance conditions, which are indicated by the TVM. Okay, so at resonance, I hope you are much aware of resonance. So if I talk about resonance, then what we can write about a formula of LC at resonance, can you tell me? At resonance, what can be the formula of LC? Simple, 1 by omega squared. What is omega? What is omega? What is the value of omega?
2 by f.
Yes, yes, 2 by f, then 2 by f whole square. Then simply we can write 4 pi squared f squared. Okay, so at resonance conditions, I'm writing here at resonance, my LC is 1 by omega squared. So thus knowing the value of frequency here, okay, and the capacitance, so we can easily find the value of inductance, right? So what in this particular parameter, if we know the value of capacitance and frequency, then automatically we can find out the value of L. Okay, so this method is somehow acceptable in the case of measurement of inductance. Okay, so now I can show you a picture. So this above method, sometimes it's not accepted. I'm telling you why. Because this additional capacitance which is introduced in the circuit because of this, okay, this capacitance. Now some errors may cause due to this capacitance. That is why sometimes this method is not taken. Now, we have to focus on the accuracy of the number of readings that we are taking by varying the frequency. In that case, suppose let us take a picture for measurement of inductance. Let me show you. Suppose I'm drawing here, okay? So this is my picture, and here it is the y-axis, it is the x-axis. I will try to plot how. See, here the frequency that I have to tell you, that is, what is the frequency here? 1 by f square. Okay, that I will put here 1 by f square. And definitely C is just like this, right? C is here. So LC is this one. So I will put here C. So C is somehow capacitor, it will be just like this. And beyond this y-axis, you have to draw a curve. How? Now, you have to extend this portion like this so that it come up like this. Okay, here you will get an angle theta, and here you will get CA. I will explain everything to you. What is CA, what is C, everything. So CU, I hope you understand, the capacitor. Okay, and is the theta angle is forming. So if I take additional capacitance, that is CA, let CA be my additional capacitance. Okay, let CA be my additional capacitance. Then what will happen? The resonance at the frequency, resonance at any frequency, you can say, resonance at any frequency will be what? First, I have only C, and then I have added additional capacitance CA. Then what it will become? C plus CA, okay, equals to what? 1 by 4 pi square f square. I hope this equation is, you have understood this equation 1, this equation 2. Okay. Secondly, if I try to find out what is 1 by f square, what will be my formula? Can you tell me? It is somehow 4 pi square L divided by, sorry, not divided by, yeah, it will be 4 pi square L C plus CA. This is my 1 by f square. Okay, and if I open the bracket, it will come up 4 pi LC plus 4 pi square LCA. Clear? This is my equation number 3. Now from equation number 3, it's very clear that if the curve is plotted between 1 by f square and C, then we get a straight line, which we am showing in this particular graph. Okay. Now the line produced back cuts the x-axis at point O dash. Where is the O dash? This is the point of O dash. Okay, this point is the O dash. So we have to check it out that the slope of the line is, what will be the slope of the line? I have got an angle theta. So slope of the line in this particular curve, I can write tan theta is equals to 4 pi square L. Okay. So from here, can I write what is my L? What is my inductance? My inductance is simple, tan theta by 4 pi square. This is my equation number 4. Is it clear to everyone? How I am able to find out L from here? So thus, knowing the value of slope of the line, the value of inductance may be obtained. Okay. Now the value of additional capacitance CA is somehow equal to if I say O dash is there, then O is somehow here. Okay, O is here and this is O dash. So you see here the range of the capacitance, additional capacitance C, that is O dash. So I'm going to the next page. Okay, now you can see here that after knowing the slope of the line, we are able to find the value of the inductance. Now, the value of the additional capacitance CA is equal to that is the intercept O dash according to this previous picture. Can you see? CA is equal to this O dash. Look into this graph. So I can move to that. I can write this. So now I can say that my CA is equal to CA is equal to CD plus CV. So what is this values? This CD is the self capacitance, okay, of the coil, and this CV is the capacitance of voltmeter. Okay, so this is my actually equation 5, which I was telling you. So from this equation 5, it is true only when the calibration of the capacitance includes the effect of the seen capacitance. Okay, so under this condition, the method, we can be able to also measure the self capacitance of the coils. Okay, so from this particular formula which I have done for you, just the previous, this formula is important. Which one? This L equals to where I wrote this one. L, you can find the formula of L here also. L equals to resonance 1 by 4 pi square f square C plus C. I mean, from these two formulas particularly, you can find out F, you can find out L. So both the formulas are important. Okay, so take down a problem from here, particularly in this context. Take down a capacitance of 250 picofarad produces resonance with a coil or with a coil at a frequency of 2 by pi multiplied by 16 to the power 8 hertz. Okay, 16 to the power 8, I think it's 8 only. My book. While at second harmonic, harmonic of this frequency resonance is produced by a capacitance of 50 picofarad. Okay, 50 pf. Calculate number 1, self capacitance. Okay, B, inductance of the coil. Okay, inductance of the coil, and neglect the voltmeter and neglect the effect of voltmeter and the capacitance and other three capacitances. So this is the question. So very easy. You are given the capacitance value. You know what is the frequency also. So from here you can easily find out the value of L. Right, because that formula is important. This formula you have to take it. This one, L C plus CA is equal to 1 by 4 pi f square. So at resonance, what is the formula I can write? At resonance, you can write. This formula is important. Take down this formula, then you can do the problem on your own. 1 by 4 pi square f square. Okay, C plus CA. This is the formula which you need, because you need to find out the inductance of the coil and the self capacitance also. So you know what is F, right? F is 2 by pi, and you also know what is your C. Your capacitance is 250, but you don't know the CA, or sorry, you don't know the CD. CD means self capacitance, you don't know somehow. Okay, so so simply what you have to do, you have to in this particular portion, you have to take this is C plus CD. Okay, because self-capacitance you need to find out CD. So CD you have to find out, and if you find out CD, then automatically you can also find out the L. So try once at your home if it's possible for you. Then we will discuss in the class. Now you can also try now also. We have some time, we can discuss. One more thing, look into the problem minutely. There are two capacitors already given, right? One is 250, one is 50. So you will write two equations for the inductance. Okay. So from two equations of inductance, you will get, then you have to compare. If you compare, then automatically you will get the value of CD. Okay. And if you get the value of CD, then automatically you can obtain the value of L. Okay. So give it a try. Check out this video and give it a try with this problem. Next class, I'll ask you if anybody has done. Even you can try it now also. Give it a try, okay? Once you try. And okay, one more thing is that suppose when we are writing this for this capacitance is 250 picofarad, produce a resonance with a coil at frequency this much. This is for the first harmonic, okay? And second harmonic, it is changing. So keep it in your mind. If you are writing for first harmonic frequency is 2 by pi, then definitely for second harmonic, it will become how much? 4 by pi. Okay, so that portion you have to also change. 4 by pi. That is why I told you, you will get two different kinds of equation. So definitely if for first frequency, first harmonic, if it is 2 by pi multiplied by 16 something, for second harmonic, it will be how much? Second harmonic will be 4 by pi multiplied by 64. Okay, just the double. Okay. So give it a try. We will discuss this problem in the next class because one formula I've told you. Let me once share the QR code if anybody has left out. 16 students are there, not 16, 15 are there. Give it a try. Use that formula. Then next tomorrow I will discuss with you. Okay, but at least try once because this question, these problems are interesting. Okay. So thank you so much for attending the class. After giving QR code, you may leave the class.